Alright, hello guys. Okay, I'm going to be going through the study guide. We're going to start with Unit 1 Physics. I can only record for 15 minutes at a time, so I'm going to try to get through this as fast as I can. So, Newton's first law is basically the law of inertia. So that means that an object at rest wants to stay at rest, an object in motion wants to stay in motion. Alright, the second law, pretty much simple. It's just F equals m times a. So force equals mass times acceleration. Later on in the packet, it will have you rearrange that equation into the other two versions of that equation so that you could solve for any of the three variables. The third law is for every action, there is an equal and opposite reaction. So, tell me whether these measurements / descriptions are vector or a scalar. So this depends on you knowing what the difference between a vector and a scalar is. So if you aren't clear, I would do some reading on that. Search up vector scalar difference, Google it up or whatever. But long story short, vectors have direction, scalars do not. Some of these you just kind of have to know. But if there is some direction aspect or you care about the starting point and the ending point, then that's going to be a vector. And if you don't care where you start or you end and there is no direction, it's going to be a scalar. So distance. Distance would be like the total amount that you traveled to get somewhere. Distance is a scalar. And I'm going to skip one because the complement to distance is displacement. Displacement is a vector. Displacement cares about where you started and how far you are exactly from your starting point. I'll show you a little bit more about that in just a second. Coming back to this one. The store is 1 mile away. There's no direction there. If I said, go to the store, it's 1 mile away, you wouldn't know where that is because I didn't give you a direction. That is a scalar. Mentioning that the store is 1 mile away, that's a scalar. There's no direction. You're driving 45 miles an hour. That is also a scalar, right? There is no direction given. I'm going to skip over to this right side here. The store is 1 mile southeast of here. Okay, so if I told you that the store is exactly 1 mile southeast, you would know exactly where to go. That is a vector because it has direction. Velocity and speed. This is a really easy one to remember. Speed starts with S. Speed is a scalar. Velocity starts with a V. It is a vector. It just so happens that it works out that way. Velocity cares about direction. Speed does not. Speed, for instance, you could be going 45 miles an hour. If I say that you're going 45 miles an hour north, that is a vector. So speaking of which, you are driving 45 miles per hour towards school. Towards school still counts as a direction. That is a vector. And then these two are kind of interesting. So Miss Woe is at the park, which is 150 feet away from her house. So my starting point, my reference point is the house. And I am over there at the park. And it is exactly 150 feet from where I am at to the park. That is my displacement. And as we mentioned, displacement is a vector. Whereas I traveled 350 feet to get to the park. I could have made this trip as long as I wanted to, honestly. Like, if I wanted to start at my house and get to the park, I could have made this trip last my entire life. I could have gone back and forth and back and forth and back and forth and back and forth 100 times before I finally made it there. And I would have traveled a much longer distance. So clearly this has nothing to do with the starting and ending point. The distance is just how far total did you go with your own 2 feet? How far did you walk, basically? So, traveling 350 feet to get to the park, that is a scalar. Okay, cool. Moving on to this page. Write all three arrangements. F equals m times a that we have in the beginning. If we want to get m by itself, we have to divide both sides by a to get m by itself. So we end up with m equals f divided by a. The two a's would cancel out. Having a divided by a is 1. M times 1 is just m. But then on the other side, we would have had that f divided by a. So m equals f over a. And very similar concept here. We want to get a by itself, so we have to divide both sides by m. So we get a equals f divided by m. Now, if we're to substitute these in, we got to look. An object has a mass of 6 kilograms and pushes with a force of 24 newtons. What is the object's acceleration? So, the acceleration is what we're looking for. It says, what is the object's acceleration? So that means we're going to use this a equals f divided by m equation that we just figured out. because we're solving for A, and we're given the force here, 24N, and the mass of 6 kilograms. You can always look to units to know which of the 3 numbers it is. So we are doing 24 divided by 6, which comes out to 4. You should include the units for acceleration, which is meters per second squared. So that is our answer. Then this one, object accelerating at 5 meters per second squared is a mass of 7 kilograms. What's the object's force? So we're solving for the force. We're going to use the first equation. We're given mass of 7 and acceleration of 5. So we simply do 7 times 5, which equals 35. And if it's the force, it's 35 newtons. An object accelerating at 3 meters per second squared hits a wall with a force of 18 newtons. What is the object's mass? We're solving for mass. We're going to take our force, we're going to divide by acceleration. So we have our force of 18 newtons divided by 3 meters per second squared. 18 divided by 3, if you didn't know, is 6. And since that is our mass, it's 6 kilograms. So applying Newton's laws, why are seatbelts important using Newton's first law? Okay, so when you are in a car, you're driving, you're going 25 miles an hour, your body's going 25 miles an hour because you're inside the car. If you stop the car, your body wants to stay in motion. It has inertia. It wants to keep going forward. Your seatbelt keeps you from continuing to go forward through the front windshield of your car. So, seatbelts help protect against the inertia you experience when you come to a stop very quickly after moving. Long story short, you will continue moving and you will go through the windshield and die. And that's why seatbelts are important. They stop you from experiencing that inertia. They stop you from going forward. If a truck and a bike both hit a wall going 20 miles per hour, explain why the truck will do more damage to the wall using Newton's second law. So, force equals mass times acceleration. We have 2 things accelerating at the same rate. One has way more mass than the other. We know that the truck is going to do more damage to the wall because the truck has more mass, and that means, in turn, the more mass, the more force is experienced by whatever it's hitting. So, the truck has a greater mass, and therefore a greater force on the wall. Explain why birds can fly using Newton's third law. Every action has an equal and opposite reaction, right? So the action would be the bird's wings pushing down on the air. But then the reason why birds can fly is that the air is pushing back up on the bird's wings. So bird pushes down on air, air pushes back up on bird in an equal and opposite reaction. Okay, a football was kicked and is already in the air. Draw a free body diagram that shows the forces acting on the football. So I'm going to use the draw tool real quick. So I'm going to just draw a circle for the ball. Bear with me. So there's the ball. I gotta make this a little less thick. So it's already been kicked. There isn't an applied force on it currently. There was an applied force, but it's not like someone's continuously pushing it. They kicked it and now they're not acting on it anymore. So there is no applied force. What there is air resistance force. Air. I'm trying my best here. Looks like fair. Gravity, of course, is pushing down on it. There's probably, like, let's say that the ball is flying this way, then there is probably air resistance hitting it from the front as well, so we could say F air we got going on that way as well. No normal force because it's not on a surface. Like I said, no applied force because they're not applying a force right at the moment. So I think this is pretty good. I think that's about it. A force is applied to the right to drag a sled across the loosely packed snow with a rightward acceleration. So, okay, to drag a sled. Okay, neglect air resistance. Draw a free body diagram showing the forces acting on the sled. So, cool. I'm gonna say, like, here's this person. I'm drawing with a trackpad, so I'm sorry if this is really bad. So they're pushing the sled. That means that there is an applied force going this way. They are pushing it rightwards. That's F app that I'm trying to write there. Because the sled is on the ground, we do see that there's that force of gravity, Fg, but then also we have that normal force, Fn, pushing back up on the sled so that it doesn't go right through the ground. We are supposed to be neglecting air resistance, but there is one more thing, and that's friction. Friction is working against us because we're pushing it towards the right, but I'm going to draw this underneath him. F frick for friction. He is pushing that, but the friction is working always against the direction of the applied force. So there is our sled being pushed. That one looks pretty good to me. Moving down to here. Wait, is my thing still going? I can't even see if the timer's still running or not. I'm trying to figure out how much time I have left on the recording. Sorry, the timer stopped working. Okay, I got about 4 minutes left. So, a car is coasting to the right and slowing down. Neglect air resistance. Draw a free body diagram showing the forces acting on the car. So the car's coasting. There's no more applied force. It's just going off of the force that it already had. So here is the car. Like I said, this is a horrible drawing, just whatever. Is coasting to the right and slowing down. Even though there is not an applied force, if it's going to the right, there's still that friction force working on it against it, going that way. So we have that friction force. We're neglecting air resistance, but obviously gravity is bringing the car down to Earth, and the Earth is pushing back up on the car with a normal force. Given this table, calculate the object's speed, distance over time. Seconds is a measure of time. Meters is a measure of distance. So this is our t, this is our d. And then it's just a change in y over change in x. So we can pick any 2 points here. We have a 0, 0 point, which is going to make it really easy on us. So let's use that. Let's use 0, 0 as one of our points, and let's use 4, 2, 4 as our other point. So if we are to do this like y2 minus y1 over x2 minus x1, this is our y. y2 is 4. Minus y1 is 0 over x2 is 2 minus x1 is 0. We end up with 4 minus 0, which is 4, over 2 minus 0, which is 2. 4 over 2 equals 2. Our speed is 2 meters per second. Answer questions about the following graph. Okay, when is the object at rest? Whenever you have a distance, and granted it doesn't actually say this, so my bad, but this is a distance versus time graph. When it's a distance versus time graph and you see a horizontal line, like this, I'm going to call this A. The object is at rest at A, at a horizontal line, because it's at 3, it's at point 3, and it stays at point 3 for the 2 seconds. It doesn't move up or down, it just stays there. So you could say from 5 to 7, like from seconds 5 to 7. When is it moving backwards? Whenever it is going from a higher point here on like our number line lower, it's moving backwards. So there's 2 points where it's moving backwards. It is moving backwards from 0 to 2. I don't know, I'll call this B. I'll call this C. So I'm going to say from 0 to 2, which is B, and from 7 to 8, which is C, it is moving backwards because it's going from a higher point to a lower point. When is it I'm sorry about my phone. When is it moving forwards? Opposite, right here, at D. It is starting at a lower position, it's moving to a higher one. So at D, it is moving forwards. It is going from 0 to 3 over the span of 1, 2, 3 seconds. When is it moving at its slowest speed? A lot of you guys got this, and I was really proud of you. When is it moving at the slowest speed? It is moving at the slowest speed at D. Even though D is the only time when it's actually moving forward, speed is a scalar. Speed does not care about direction. It doesn't care if we're going forwards or backwards. It cares how fast. D has the lowest slope, so D is where we are moving at the slowest speed. You can see that B and C are steeper. Even if we're going backwards, it doesn't matter. The steeper the slope, the faster we're going. The less steep the slope, the slower we're going. So at D, it is the slow speed. Okay, cool. Oh, calculate the velocity for the first segment. Let's do this from 0 to 2. Okay, so similarly, we have 2 points here from 0 to 2. This is our first point, 0, 4. Our next point is 2, 0. We do y2 minus y1 over x2 minus x1. So we got our y2, 0, minus y1, 4, over x2, 2, minus 0. That's our x1. So we got negative 4 over 2, which is negative 2. Our velocity for the segment is negative 2. Boom.